Alright, good morning. Today is Thursday, June 24th, 2021, and we are going to do another LeetCode problem. Yesterday we did an in-order traversal of a binary tree, and we learned quite a bit about what we didn't know before. So in order to traverse a binary tree, we have to, in order to perform this, to return the correct solution, we have to do three things. We have to traverse the binary tree in the right order. We have to manipulate the data in a way that produces the right result, and we have to return the data in the correct order. And I didn't really understand that in the first, in this last problem. We're going to go to binary tree preorder traversal, and we'll try it again to sort of test our knowledge about binary trees. Okay, given the root of a binary tree, return the preorder traversal of its node's values. So, preorder traversal, in this case, it's not a binary search tree or anything, so I'm just going to put in node values here. 2, node 3, put a 4 in, 5, 6, and then 7 for our nodes. So in preorder traversal, as we traverse the tree, the order that we need to do is, and this is just as a definition of preorder traversal, this is pretty basic algorithm stuff that's just expected to be part of the vocabulary of any developer. So for preorder traversal, the order that we will return the node values is left, middle, right. So, to traverse our tree, it would look like we call preorder traversal on the root, and the order is left, which will evaluate 2, while the preorder traversal call on 1 remains in the stack, partially executed. We will, again, recursively call preorder traversal on 2, and that will stay on the stack, and that will cause us, and during the preorder traversal of 2, we will then evaluate 4, which is a leaf node, which will have no children, and thus return 4, returning us back to 2. So the first thing we do is we return 4. 2 will then return, and then preorder traversal on 2 will call preorder traversal on 5, which has no left child. It will return 5, and then evaluate no right child, and then return up to 2.
Oh.
Excuse me, we just did an in-order traversal. Okay, let me go back. What will happen is we'll traverse 4, return to 2. 2 will then evaluate 5, which will have no child nodes. And after it evaluates both of its child nodes, it'll return 5. Now we go back to 2, which, having evaluated both its child nodes, will return itself. I think this is post order, isn't it? One, 2, 3. Oh, yes. it evaluates itself first. So 2, 4, 5. 1, 2, 4, 5, 3, 6, 7. And that's the order returned by preorder. So the things we have to do is, let's do our to-do. Visit each node in the correct order. We have to perform any required operations on each node, and then you have to return the requested return type. Okay, cool. So here we are doing preorder traversal on prenode root. Okay, the recursive solution is going to look something like this. We are going to if root equals null, we need to continue. Or no, excuse me, we need to return and then we need to do store a list somewhere. And I think we have to store it outside of preorder traversal, outside of the function. So it'll be mostly recursive, but can't be completely recursive. We'll define a mutable list with type variable integer and instantiate it. And that will be our constant value, mutable list of. For preorder traversal, we do list add root value. We'll recursively call the function on the left node. And then, oh, excuse me, we'll recursively call preorder traversal on the left node, and then finally on the right node. And then we'll return. We'll return list. Okay. Cool. So we start with an empty list. We have our preorder traversal function, which will be called by the test environment, and a nullable tree node of called root will be passed to it. The return type is a list of ints. So as we traverse the tree, if root equals null, we will return the list. As we go through, we will add to the list root value, the value of the current node, and then we'll call preorder traversal on the left, add the node to the left, call preorder traversal on the left, add 4, add to child node, which has a value of 4. 4 will return itself, and then execute preorder traversal on its children, which are both null. Preorder traversal left is null, which, as it's called, if root is equal to null, it'll return list to 4, which it doesn't care if it's null, and then it'll do likewise with right. 4 will return up to 2, 2 will execute the same process on 5, and then 2 itself will return to 1, and 1 will then execute a similar function on the right subtree, whose root is 3. So it will go 1, 3, 3 will be added to the list, 6 will be evaluated and added to the list. The children are both null. It will return the list so far to 3. And then do the same thing to 7. And then 7 will return to 3. 3 will return to 1, and 1 will return to the test call to the environment, which will now contain the list of all the numbers we're interested in. Okay, so this is a pretty simple solution. Return list at the end. Looks like we have all our correct data types. And this is a recursive solution. Let's see, I don't see there are any compile errors at this point. If root equals to null, return list. List, which is of type integer, is returning the value of the root, which is a tree node. So integer is being added to the integer list, mutable list. And then preorder traversal is being recursively called on the left root, which is nullable, and the right root, which is nullable. Okay, at this point we'll execute our solution, see what we have. I'll have to get the button off my webcam real quick here. Run the code, any compile errors? Looks good. Let's run all the example test cases. Looks good. Let's try an empty list. Empty. And let's try 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4, 5, 6, 7 as our input. Our output is 1, 2, 4, 5, 3, 6, 7. Okay, this looks pretty good. I think we have a firm grasp of how the recursive solution works. I'm going to go ahead and submit it and see if we pass. We do. Really low memory usage, really low memory usage, average runtime. So the solution is straightforward. I'm guessing most developers that do this use a pretty similar approach with maybe a thing or two different. The challenge in the description was to see if we can do the same thing iteratively, which we can, and I would like to do to test my knowledge, using a queue. Now, I need to figure out how to reset this code here in LeetCode. We'll reset to the default code, and we'll attempt the same problem iteratively, which will involve using a stack of sorts. Now, the stack data structure itself in Java is really old, and I've read that it's suggested that instead we use an array deck. So we'll instantiate. So we'll define a function deck, and deck means double-ended queue, which is a data structure which allows easy access to both the head and the tail of the queue. So it can function both as a stack or a queue. In this case, we're going to be using it as a stack. So value queue equals array deck containing type tree node, the nullable type tree node as the type variable. Capitalization camel case looks good. And then we will instantiate it in the top level declaration of solution. No, we don't need to do that. We don't have to keep it as a field in solution. We can put it as within the scope of preorder traversal, because we're doing this iteratively. Okay, now let's take a look at what we need. Because we're doing it iteratively, we can assign our value list. Oops. And the list we will assign type mutable list of type int, and we will instantiate it, and the inferred type will be mutable list of type int. Okay, cool. Now, because preorder traversal is requesting a return of int, return of list of ints, we will return our value list, which will be implicitly converted from a mutable list into a array list. Not sure. Yeah, I believe a list is an array list. Okay. So now that we're doing this, we need to add root to our array deck. And then we'll do a while loop. I believe add adds to the end of the queue. But the deck also contains a a method add last, which explicitly adds it to the end, which is more readable. So we'll do that. Deck add last, and then we will set up our control loop. While deck is not empty, so we call the method is empty. The infix method is empty on our deck variable, our deck value. And deck last, I believe we can call last, is not equal to null. Val node equals deck remove last. So we're assigning a value of node equal to the return value of deck remove last, which will return a nullable tree node. So the inferred type of node is nullable tree node. If node equals null, we have to do our null handling first. We will continue to skip to the next. No. Yes. If the node is null, we will continue, which will skip to the next loop in the while loop. So we are removing our last, so we are emptying the deck every iteration. If we do pass a null root, the node will be null, and we will just continue, and then the next time oh, actually we don't need to call this because oh boy. Okay, yeah, we did our null check wrong, didn't we? Because as we traverse the tree, some of the nodes will be null. So we have to remove the check for deck last. It's not equal to null. We know the deck is not empty. But we don't know that the last is not null. So after checking whether the deck is empty, we check whether the last is equal to null, and if it is, we continue, skipping to the next iteration of the while loop. Okay, that looks good. At this point, we'll define an immutable value node and assign it to the last value of the deck, which again is a nullable type tree node. We've already checked that it's non-null, so the value of node will have inferred type tree node instead of a nullable tree node. So then we can perform operations on node for the rest of the while loop, knowing that we won't return a null pointer exception, or won't throw a null pointer exception, excuse me. Okay, at this point, we will do our operations on the node itself. So the first thing we need to do, since it is a pre-order traversal, we will add to the list the value of node. Then, in our recursive solution, we did a recursive call on the function preorder traversal. In this case, we will not. Instead, we will add. We'll take the deck, and we'll add the left child of the node to the deck, and then the right child of the node to the deck. This will give us a breadth first tree traversal. And it looks very similar to our previous solution within the while loop. But while the last one was depth first, this one is breadth first. Is it? No, it's not. It is a depth first, because it's pre-order. Let me think. Let's talk our way through this. Make sure we have the correct solution, or see whether our current solution is correct. We'll make our tree. Two, three. 4, 5, 6, and 7. So what we expect for our preorder traversal from the previous example will be 1, 2, 4, 4 will return to 2, and 2 will then evaluate 5, which will return to 2, which will return to 1, which will evaluate 3, which will evaluate 6, and then lastly 7. 6 will return to 3, and 3 will evaluate 7. 7 will return to 3, 3 will return to 1, 1 will return to the calling function from the test environment. Okay, so this is what we expect. Let's walk through our algorithm, see what we have. It may be incorrect. For our deck, we will add 1. Then we will add 2. No, this is wrong. The answer we'll get would be 1, 2, 3. So the nodes will be traversed in order 1, 2, 3, 4. No. Yes. Then 2 will be called. 4. 5. Okay, so the roots, the tree will be traversed in order, but as we traverse the tree in order, after our first while loop, we will have traversed 1, where we will add 1. We'll add 2 and 3 to the deck. So now our deck contains 1, 2, and 3. One will be traversed. Then we'll reset the while loop and pop the last value off the deck, which is non-null. List will add 2, and then the deck will contain 4 and 5. At which point 2 will be eliminated. The next element in the deck will be 3, which will return 3. And it will add 6 and 7 to the deck. 4 has no children, 5 has no children, 6 has no children, and 7 has no children. Okay, so our approach is wrong. Can we fix this quickly? list add 1, 2, 4. Okay. So we have to. I'm thinking about quitting right now, and checking the solution. But we'll think about this one last time. Just see if we can understand how to use a deck to solve this, if we can use that as approach. Well, we could pop the deck right here, right immediately after adding left, but that would be the exact same thing as doing a recursive solution, which is maybe what they're asking. So we'd have to remove last and then do a quick null check. And then I don't know. We're going to take a look at the solution and see what they say, and then we can go through the solution together. Okay, general strategies. There are two general strategies to traverse a tree: breadth first and depth first. Depth first can be distinguished as preorder, in order, and post order. Depth first, breadth first, 1, 2, 3, 4, 5. So depth first can have 3 strategies. So we have mastered the recursive solution. Okay, let's take a look with the head. While stack is not empty, I used a stack instead of a deck. It shouldn't make a difference. Node equals poll last. We did our null checks. Apparently they did not. So if a null is passed here, tree node will be null. We'll add node value. Oh, here. This is where they did the null check. They did a separate null check on top. Okay, so really, what happens if we run this? Oh, okay. Well, we already checked deck. We already know the deck last is non-null, and we know it's non-empty. However, only safe or not or non-null asserted calls are allowed on nullable receiver of type tree node. So we'll assert it's non-null because we know it's not null. Non-null. Okay, we'll run the code. I believe it's okay now. Null pointer exception. What? Oh, wait a minute. Can a deck not contain null? A deck can't contain null. And then we have to do the null check here since we can't add a null to the deck. Okay. Wrong answer. Yep. Expected is 1, 2, 4, 5, 3, 6, 7. What is different here? Well, deck is empty. This becomes redundant. This is the same. One, 3, 7, 6, 2, 5, 4. So we're backwards. Why did they add right first in preorder? If node left is not null, add. Okay, so list add node val 1. If node left is not equal now null. Oh, we're removing the last. I was removing the first. And I believe this should produce the right answer. Nope. Oh, okay. And this should produce the right answer. Okay. List, right, left. Okay, so following this algorithm, we start by returning 1. We're putting 1 in the stack. And as we iterate through the stack, one is in the list. So the stack will then contain 3 and 2. 2 will be evaluated next. Because we're removing the last from the stack. And the root is 2. Two will then add 5 and 4 to the stack. Four will be removed from the stack and processed, so 4 will then be added. 4 has no children, so we'll skip adding right and left to the stack. It'll skip adding those nulls, and then 5 is on the stack. 5 will be added to the list as 5 is evaluated from the top of the stack. And as 5 has neither children and left or right, it will continue through the while loop. The deck is not empty. At this point, we'll remove 3 from the deck and evaluate 3. Node is now 3. We will add 3 to the output. And then we'll add 7 to the stack and 6 to the stack. We pop the last value off the stack. 6 has no children. We'll pop 7 off the stack. You popped 1 off the stack already. And now the stack will be empty. And we will return our list, which will be 1, 2, 4, 5, 3, 6, 7. Cool. Let's run our test cases. Okay. And submit. That's a little faster. Cool. Okay, so what did we learn? We learned that decks can't contain null. That means we want array deck of non-nullable type tree node nullable type for deck. So that's something very important we learned. and we learned that depth first searches are pre-order, in order, and post order. Okay, we learned we can mirror pre-order by reversing of to the deck. Cool, yeah, we learned a bunch. Decks can't contain null. We'll learn that again. Awesome. Cool, we'll call that good for now. That's an hour of LeetCode. And we learned a bunch about pre-order traversal. Awesome.